previous lectures, we've looked at applying bit masks with bitwise logical operators to evaluate and manipulate bits of our data. We even went so far as to make up an interface for a peripheral piece of hardware and then write code that would control it using the bit masks and bitwise logical operators. In this video, what we're going to do is learn to make really nice bit masks, to define our bit masks in very clear ways, unlike the use of the raw hexadecimal immediates that we had done in the past. So to get started, I want to look at a line of code. So normally, I wouldn't have put this comment above, but for the real estate interest horizontally, I put it above. But let's look at this mask. So here's a constant unsigned integer mask of some fairly complicated nature. And what's wrong with it? Well, there's a couple things wrong with it, first of all. This is hard to read. BAE5. It's not clear what bits this thing is actually going to manipulate. Luckily, the engineer who wrote this code was savvy enough to realize this and added a comment that included the bit string. Unfortunately, this bit string has 17 bits in it, and instead of 16 bits, which appears to be the nature of this particular hex mask. But there's still a couple more. There's still another problem. So one, it's hard to read. Two, the mask and the comment are not equivalent to one another. But is this machine even 16 bits? Right? It may have been written for a machine that was 16 bits. And so we created a library that worked for this specific processor that our startup company has been using in all of its products in the early days. But then time goes on, and you've got this library sitting here, and then people start to upgrade the equipment that they're building on top of. So your startup isn't a startup anymore, and now it's using 32-bit and 64-bit hardware. Well, what's going to happen with a mask like this? Well, remember, we want ones in certain positions and zeros in other positions, and it depends on the operations we use. If we do an AND where there are zeros, then we're going to end up turning bits off of things. So consider this code that was clearly written for a 16-bit machine, or at least with the intent to run on a 16-bit machine. What happens when this runs on something bigger than 16 bits, say 32 bits, 64, or 128? Well, what's going to happen is the high-end bits are going to be padded with a bunch of zeros. We know there'll be zeros because this is an unsigned thing, so we won't sign extend or anything. But this is just going to set some of the bottom bits, which means a bunch of the higher bits are going to be zeros. And if we apply this bit mask with an AND operator, we might be turning off a lot more bits than we intended, and that could have terrible unintended consequences. It could also have very subtle unintended consequences that would be extremely difficult to nail down over time, since the mask would seem to indicate, after we calculate its binary, that it manipulates the correct bits. But the issue is that the size doesn't match the machine it runs on. So what we need is a way to replace a mask like this with some other form of definition that makes it clear which bits are set and that all the other bits are not, and that will work regardless of whether this machine is 16 bits, 32, 64, 128, whatever it may be. So we have to build up a skill set for this. So to start, let's look at the simplest operation that will help us. If I make a bit mask like this, hex, and again, we'll just pretend 16 bits for a second. Let's say I make a bit mask 0, 2, 0, 0. Well, what is this on a 16-bit machine? Well, the bottom bits here are all zeros. So 1, 2, 3, 4 nibbles. Zeros in the bottom nibble. 1, 2, 3, 4 zeros in the next nibble. Then we have a 2 in 4 bits. So 0, 1, 0, 0. And then we have a bunch of zeros. 1, 2, 3, 4. All right, so here's each of those 4 hex characters. So this is all zeros with a 1 in a specific bit. So here's bit 0, here's bit 4, and then here is bit 8, and here's bit 9. So this is a 1 in bit 9. Now it would be great if instead of hex 0200, we said 1 in bit 9. And we can. And the way we do it is like this. We write a 1, and we left shift it 9 times. Okay. Now let's break this down. First of all, when we write something like this, this 1 is really equivalent to the bit pattern, lots of zeros with a 1 at the end. And that's true regardless of whether this machine is 8, 16, 64 bits or anything, right? So now if I left shift this 9 times, what's going to happen? Well, I'm going to end up with 0, let's say again 16 bits. Well, I'm going to end up with this thing up here. And the reason is there was a 1 down in the right bit, and then it was shifted left once, twice, 3 times, 4 times, 5 times, 6, 7, 8, and 9 times. So 1 left shifted 9 times is equivalent to saying there's a 1 in bit 9. And we can generalize this by saying we'll take a 1 and left shift it k time, and that puts a 1 in bit k. And when we say bit k, we really mean the bit that's equivalent to 2 to the kth power. All right, now what if we wanted to have more than a single 1? Right? Let's say we want to put ones. Sometimes I'm making my ones with the flags or the serifs, and sometimes I'm not. I'm confused by this. Put ones in bits. We'll just do 2 bits here. But let's not make them touch each other. Or we'll make it totally arbitrary. Let's say bits A and B. Well, how are we going to do that? Well, it's going to involve this, but this only puts 1 bit into a particular location. It puts a 1 in bit K. So let me at least do that twice. So I'll take a 1 and put it in bit A. And I'll take a 1 and I'll put it in bit B. So these work individually for putting a 1 in bit A and a 1 in bit B. But I need a 1 in both. Now if we pretend we have bit patterns, let's say A is 3 and B is the number 7, and then just for simplicity I'll make this example have 8 bits in it. Then I'll have A being the bit pattern 0, 1, 2, 3, 4, 5, 6, 7. And B will be 0, 0, 0, 0, 0, 0, 0 with a 1 in bit 7. I don't mean B is this, but 1 left shifted B, and this is 1 left shifted A. If I OR these together, then 0 or 1 is 1. 1 or 0 is 1. And the rest is 0 or 0, which is 0. And now I have a 1 in bit 3 and a 1 in bit 7, or a 1 in bit A and a 1 in bit B. So the clear thing that we need is an OR. So if we want to write this kind of code, then we can just say 1 left shifted A, ORed with 1 left shifted B, and we will just forever read this as 1s in bits A and B. Now, this gets a bit unruly once we get past 2 or 3 bits. We don't want to have 1s in bits 2, 3, 4, and 5, and 6, and do 1 left shifted 2, ORed with 1 left shifted 3, ORed with 1 left shifted 4, OR with 1 left shifted 5, OR with 1 left shifted 6, and so on. That's just annoying, if nothing else. So we need a way to deal with runs of bits that's a little more efficient in communicating what it does. So let's take a look at how we do that. Let's say, get another sheet of paper here. Let's say we want, I don't know, 5 1s starting at bit 0. So this is pretty simple. That means 5 1s all the way to the right, And I don't say how big this is because I want it to work no matter how big our particular system is. Right? We assume it must have enough bits to hold 5 ones starting at bit position 0. But the way I write this would look like this. I'd say it's the inverse of 0 with a capital U afterwards, left shifted 5 times. All right. So this is going to create my bit mask. And at first, this may look absurd. But if you follow along with me, it won't be so bad. And after a while, kind of like the Matrix, you start to just see these immediately for what they mean because you use the same pattern of description every time. So how does this work? First of all, you may or may not be familiar with the use of this capital U after a numeric value. Whenever you use a raw numeric immediate like 0, it's going to be treated as a signed integer. And whenever I start doing some things with 0 and shifting to make bit masks, I will do right shifts from time to time. And we have to be careful with those right shifts that we're doing them with unsigned values, or we may accidentally end up with bit patterns we don't want because of sign extension. So as a habit, I always do these kind of bit masks by saying that 0 is unsigned. By putting the U there, we're typecasting 0 as an unsigned in. So what is 0? Well, it's a bit pattern that looks like this. Right? Bunch of zeros forever. What happens when we invert that? Well, we're going to get a bunch of 1s in all of our bit positions. Okay, so then let's left shift that 5 times. Well, the good thing about left shifts is that they'll create a vacuum to the right of this many bits, so 5 bits big. So we're going to have a bunch of 1s, and then there'll be 5 zeros at the end. Right? And we know that that vacuum will be filled by zeros because they're on the right end or the lower order bits. We only have to worry about a sign extension if it's up here on the high end that the vacuum is created, and if our data type was signed, which it isn't. We've protected ourselves from that accident. So now we've got this, which is a lot like the bit pattern we want. We want a bit pattern that has 5 1s starting at bit 0. Well, this has 5 zeros starting at bit 0, and everything else is 1s, no matter how big this is. So if we invert this, we end up with all zeros and 5 1s starting at bit 0. All right, so let's do another one of these. What if I want 7 1s? Like the 7 matters. 7 1s, but starting somewhere other than bit 0. I want these to start at bit 3. All right. Well, it's going to look a lot like this. It's going to be a bit pattern that has 7 1s in it, and I'm going to acquire this practically the same way. So right now, this is the same as this, except instead of 5, I've got a 7, which means by itself, this will generate a bit mask that has all zeros and then 7 1s. 1, 2, 3, 4, 5, 6, 7. That start at bit 0. But I need them to start at bit 3. So what I want to do is relocate all of these 1s over. So I want to move this one 1, 2, 3 times over so that everyone before it can go 1, 2, 3 times over, because then it'll be this one here will go from position 0 to bit position 3. So if you recall when we did 1 left shifted 3, that puts a 1 in bit 3. We're moving this one to bit 3, and everything after it will be the next bit higher. So I just left shift this 3 times. Now I have some zeros followed by 1, 2, 3, 4, 5, 6, 7 1s, preceded with 3 zeros, so that the first or the lowest one is on bit 3. And this will work regardless of how big that system is, whether it's 4 bits wouldn't hold 7 bits, but whether it's 8, well, couldn't have 8 bits either because you wouldn't have 7 ones starting at bit 3. But as long as there's enough to hold this pattern, 16 bits, 32, 64, 128, 1024 bits, doesn't matter. This little bit of stuff here, which is just a use of bitwise operators, is going to dynamically create this to fit it. Now, when I say dynamic, I want to be extra clear. I don't mean that at runtime, this thing is generating bit masks on the fly that fit your current machine. If they did, then this would be potentially inefficient because there's a lot of operators that are happening there. But that's not what's going to happen, because if you peek here, each one of these operators is working on an immediate value like 0 or 7 or 3. And that means your compiler is going to pre-calculate the result of the entire expression. So at runtime, it'll be no different than if you had supplied a hexadecimal immediate in terms of runtime performance. There'll be no extra performance hit associated with this. So it reads well, works dynamically on for recompiling from architecture to architecture to architecture, regardless of the size, and you don't get a performance hit. What could be better? So let's try some more. Go to a new sheet here. Trying to get these weirder as we go. Let's say I want ones in bits. Let's say weird, something weird. 4, 7, and 12 through 15. So I'm describing this in a way that's not uncommon here for interacting with pieces of hardware like we did with our typewriter. Here we have bits identified as from 12 to 15. Now really that's bits 12, 13, 14, and 15. So that's 4 bits starting at 12, but that's not often the way the information is provided to us. So we're going to work with it this way. How do I make this thing? Well, I want a 1 in bit 4, so 1 in bit 4. Then I'm going to combine that with a 1 in bit 7, so I'll OR it with a 1 in bit 7. Now, technically, these parentheses are not necessary, but I have personally found, depending on who you're working with and the editor and fonts involved, that the OR right next to a 1, particularly if you don't provide any white space here, can become confusing looking. You may misinterpret it as the double pipe. And so I always like to put a little white space between my operators, and then for this particular idiom I add parentheses out of just basic coding standard on my own part. Now when I do the next one, I'm going to OR it with a bit mask that has 1s in bits 12 through 5, which is really 4 1s starting at bit 12. So that's just like what we've done before. I'm not going to put this one entirely in parentheses because I won't need to, and I won't have any visual issues with this pipe. So I'll invert the inverse of 0 unsigned, which is left shifted 4 because I want 4 bits from 12 through 15 inclusive. But I want them to start at bit 12, so I left shift that part 12 times. Now here I may have all this stuff and just feel like it's not clean, so I'll add parentheses just for the sake of it. But that's it. There's a bit mask that has a 1 in bit 4, a 1 in bit 7, and then 4 1s in a row starting at bit 12. And we could verify that by walking all of that out, but I'll let you do that on your own time as an exercise. Or let's do one more, something different. Maybe instead of all 1s, I want 0s. And maybe instead of the left-hand side, I want something on the right. So let's say I need a bit mask that has 0s in the high 6 bits. And of course, the high 6 bits change their actual position numbers when you move from, say, an 8-bit machine to a 16 or 32-bit or 128-bit machine. So we still want a bit mask like these that will tell us exactly what's going on, as well as work when we upgrade the hardware or downgrade it, as far as that goes, from system to system as time progresses. So in this case, I need to get 6 of something. So here I got 4 of something. So I want to do the same kind of thing, but I don't want it to be on the left or the right end. I want it to be on the left end, the high bits. So I'm going to use the opposite directional shift. So if I start with 0 unsigned, if I were to right shift that 6 bits, well, it would just bring in a bunch of zeros and I'd still just have all zeros. So I need to invert this first. So now I have a bunch of 1s. If I right shift this 6 times, I'll go from all 1s indefinitely to 6 zeros that fill the vacuum, 1, 2, 3, 4, 5, 6, followed by all 1s indefinitely. So here's my simple bit mask for zeros in the high 6 bits, 1s everywhere else. All right, so now we know how to generate superb bit masks. Let's go back and look at our programmable typewriter peripheral device that we manipulated in an earlier video and redefine all the bit masks in these terms rather than just using those hexadecimal immediates. So let me return a sheet of notes from the past here so that we can copy this correctly. Originally, what we had was this. So we had up here in the sign bit, we had something, then we had bit 9, bit 8, and then 0 through 7. And these were all unused over here. Here's bit 8, here's bit 9. All right. And this is the busy bit to find out whether the printer or the typewriter is doing anything. This here is the feed bit that causes the device to eject the paper. Here's the strike bit. That when toggled makes the key whoosh, strike and print whatever letter is contained in the bottom 8 bits. So last time when we looked at this, we defined all of these masks in hexadecimal. So what we want to do is just eliminate that entirely. We won't even look at those except for one more time for a simple example because I just noticed it. Here we were assuming that we were running this on a 16-bit machine. This bit mask here, the busy one, that's a 1 followed by all zeros. However, this one is definitely in bit position 15. So if we were to suddenly go from a 16-bit computer to a 32-bit computer, this bit mask would have the 1 in the wrong bit because this says put the 1 in the sign bit. So we definitely don't want that hexadecimal style. So again, we'll start with the stuff on the low order bits and work our way up. So the letter mask, we would have had said that this is an unsigned constant int, for example. That letter mask needs to get set to a bunch of 1s from 0 to 7. So that's 8 1s starting at bit 0. Easy. That's the inverse of 0. Left shifted 8 times because we want 8 bits. And if we don't put anything here, then it starts at bit 0. I, however, prefer by standard to go ahead and add that we're left shifting this 0 times, which does nothing. But again, this doesn't happen at runtime, it happens at compile time. But it means that every time I see something that looks like this, it always says how many bits and where do they start. And so this is nice for me. All right, so that's the letter mask. What about the strike mask? Well, this one's going to be easy because it's a single bit in position 8. So 1 left shifted 8 times. will give us a 1 in bit 8 and zeros everywhere else. Feed. That'll be a 1 in bit 9. So we just left shift it 9 times. And the busy bit is different, however, because it's in the high order bit, the sign bit, not bit 15. We always want to make sure it's the sign bit because for some reason that's what, the whack job that invented this printer or invented this typewriter decided to do. So here we'll have to shift in the right direction. So we'll start by inverting 0 and being careful to make sure it's unsigned so that we bring new zeros in. And we'll right shift it 1 time. So this is all ones. The inverse of 0 is all ones. Right shifted once is a 0 in the 1 bit of vacuum with all ones after that. But we need a bitmask that has a 1 in the sign bit followed by all zeros. But that's just the inverse of this. So now I can invert it. Now again, I'm going to reiterate that up here I also put in the left shift to say where these bits start. And I did not yet do that down here, but I can. And then there will be a visual distinction between these lines of code because of the direction of those double carets. So if I do all of this so that we now have, let's see, 1 with all zeros, I could do another right shift out here and that would relocate the high end of this 1 to some other bit location. So it would tell me how far down to go. So we could either leave it like this with a semicolon, or if we wanted, we could optionally say to right shift this 0 times. But that's optional on this one. I always do it up here because I do that so frequently. I rarely do the right shift unless it's just to put things in the high order bits, in which case I might not put this at all because then it will be very distinctive looking. Short, long, right? And then I'll have a clear indicator that 1 is going to the right and dealing with things on the high bits, and 1 is going to the left and dealing with things on the low bits, let's say. So that's how you write superb bitmasks, and I strongly encourage you to use this technique instead of using hexadecimal numbers. And if you don't want to use this technique, or your language doesn't support this kind of thing, or your compiler doesn't, then definitely use hexadecimal. Do not ever, ever use decimal numbers as immediates to represent masks, because decimal numbers show up in code all the time, and they mean whatever number they mean. So when you have a decimal 3 on a line of code, it probably means the numeric value 3 and not the bit pattern 1, 1. And if you use a decimal bit mask in this way, it's going to confuse your reader, whether it's you or some other engineer down the road. You'll confuse them into not seeing that this is a line of code that's doing some bit twiddling. If you've got any questions, please leave comments below, and I'll see you in the next video.